Alright, in this video we're going to take another look at some acid-base titration word problems. So you remember that an acid-base titration is an experiment where you're using a burette to deliver a titrant, the liquid in the burette, which can be a base or an acid, and it's being delivered into a flask that contains the opposite. So if you're using a base as your titrant, you'd have an acid in your flask, and that's technically called the analyte. If you had an acid in the burette, you'd have a base in the flask. So this first question says to complete the data table for the standardization of sodium hydroxide using potassium hydrogen phthalate. You remember that the word standardization simply means determining the concentration of accurately. So we're trying to find the concentration of sodium hydroxide, and to do that we're titrating a sample of potassium hydrogen phthalate, which is a monoprotic acid, if you recall from our lab. It's a pure acid, so it's called a primary standard. It's guaranteed pure. So in this experiment, the student used 0.6073 grams of KHP. The molar mass of KHP, potassium hydrogen phthalate, is 204.2 grams per mole. So stop and figure out the number of moles of KHP that you used. Well, to do that, I'm simply going to use my little formula that moles is equal to mass divided by the molar mass. Alternatively, you could use a unit multiplier if you prefer. So to take the mass, 0.6073 grams, divide by the molar mass, 204.2, I'm going to keep 4 digits in the answer because there were 4 sig figs in the mass and 4 sig figs in the molar mass. So the number of moles, a pretty small number, 0.002974, 4 significant digits. All right, the number of moles of acid. Now, once you've got the moles of acid, we're being asked to find the moles of the base, the sodium hydroxide. When you need to go from moles of one substance to moles of another substance, you need to look at a balanced chemical equation because this is really a stoichiometry problem. The acid, KHP, was monoprotic, so we can simply call it HA in a balanced equation. Remember, KHP is not a chemical formula. The P there stands for phthalate, which is really a big, ugly chemical formula with carbons and hydrogens, oxygens. So we'll just call it HA because it's got one hydrogen. It reacts with our sodium hydroxide, NaOH. It was essentially a double replacement reaction. This is called an acid-base neutralization reaction. The hydrogens and the hydroxides will make water, and then we get a salt, sodium A. This is really sodium potassium phthalate if you look at the original name of the acid. The key from this balanced equation, though, is that the acid and the base react in a 1-to-1 ratio. So the moles of acid and the moles of base are going to be equal. If we've used 0.002974 moles of acid, because of this ratio, we're going to need to use 0.002974 moles of the sodium hydroxide. Of course, you could set up a unit multiplier, this many moles of the acid, HA, and with your unit multiplier convert moles of HA into moles of NaOH, and you'd be using that 1-to-1 ratio in your multiplier. The volume used, well, that comes from the initial and the final levels from the burette. So they finished at 28.46 mils, so 28.46 minus they started at 4.71 mils. So the difference is what they've used, 23.75 milliliters. Convert that to liters by dividing by 1,000, 0.02375 liters. And finally, to get your concentration, you remember that concentration is moles divided by liters, C equals N over V. So we take the moles of the base and we divide by the volume of the base in liters, 0.002974 divided by 0.02375, and we're going to keep 4 significant digits, 4 digits divided by 4 digits, 0.1252 moles per liter. Question number 2, more of a word problem. tells us that another primary standard, in addition to potassium hydrogen phthalate, was potassium hydrogen iodate. And it's got a slightly different chemical formula. A 0.403 gram sample of that primary standard required 32.91 milliliters of calcium hydroxide for complete neutralization. Pause the video and see if you can write down a chemical equation, a balanced equation for that acid reacting with the base. When you're writing your equation, because the acid is monoprotic, we'll just call it HA in the balanced equation. So go ahead and write the balanced equation. So HA, the acid, reacts with calcium hydroxide, the base. And what I've recommended you do in class is that you look at the acid and it has one hydrogen, it's monoprotic, but the base has two hydroxides. So what I suggested in class is that you start by making the hydrogens and hydroxides equal. So we're going to completely neutralize the base, so we're going to neutralize both of these hydroxides. That means we need 2 moles of the acid to do that. Now we have 2 hydrogens and 2 hydroxides, they're equal. A hydrogen and a hydroxide combines to make water. So if you have 2 hydrogens combining with 2 hydroxides, you're going to create 2 waters. And then whatever's left is going to be the formula of a salt that is also produced. So calcium and 2 of these A's. Calcium is the cation, so it goes first, so CaA2 would be the formula of the salt being produced here as well. Now we want to take a string of unit multipliers to find the concentration of the calcium hydroxide solution. So what we're going to do here is, with a string of multipliers, what we were doing up here in a series of steps in a data table, and we're going to end with the concentration of calcium hydroxide. The hardest part of this is figuring out what to start with, given all the information in the problem. One rule of thumb is to not start with a unit multiplier. And in this problem we're looking here, we have a mass of the acid, and we have a volume of base being used. I don't really see a unit multiplier there. So of those 2 numbers, which one do you think we might start with in this string of unit multipliers? Well, you might ask, well, which of these could I go somewhere with? For example, if you start with the volume of the base, really the only thing you could do would be to convert that to liters, and then you wouldn't be able to do anything else. On the other hand, if you start with the mass of the acid, we could use its molar mass to find the moles of acid. Then we could use the balanced equations ratio to switch from moles of acid to moles of base, and that leads us somewhere. So by that logic, we'll take the mass of the acid as our starting point, 0.403 grams of the acid HA. So now let's think about what we can do. Okay, the first unit multiplier, we can switch our grams to moles of HA, and that would be using its molar mass. Then, once we have the moles of HA, we can convert the moles of HA, the moles of acid, to moles of our base, which was calcium hydroxide. And that will come from the ratio in the balanced equation. That's the stoichiometry part of the calculation. Now, once you have moles, you're trying to find concentration. So you remember moles, or concentration is the moles divided by the volume. Now, technically, the volume should be in liters, but what I'm going to do here is just go ahead and divide by the volume, which was given in milliliters. So I'll divide the moles of calcium hydroxide by the milliliters of calcium hydroxide. And then with one last multiplier, I'll convert those milliliters. Since they were on the bottom here, I'll put them on top there to cancel. And I'll switch those milliliters to liters. So now when you look at this, you're going to have the grams canceling. You're going to have the moles of acid canceling. And your milliliters will cancel. And what's left will be the moles per liter of the calcium hydroxide, which is what we're trying to find, the concentration. So the first multiplier is the molar mass of the acid, which was this potassium hydrogen iodate. So let's grab a periodic table if you have to, and look up some molar masses. So potassium is 39.1 plus, we have one hydrogen, 1.01, plus 2 iodines, so 2 times 126.9, plus 2 times 3, 6 oxygens, so 6 times 16. The molar mass is 389.91, so 389.91 grams per mole. From the balanced equation's stoichiometry, 2 moles of the acid reacts with 1 mole of the base. And now we've got moles of base. We divide by the volume, which was 32.91 milliliters. And then we switch the milliliters to liters. There's 1,000 milliliters in a liter. All right, so now the rest is just grabbing a calculator and evaluating that. 0.403 divided by 389.91, and then divide by 2, divide by 32.91, and times by 1,000, we get 0.0, how many digits should I keep? 3 digits divided by 5, divided by 4. We're going to keep 3 digits in the answer. 0.0157 molarity is the concentration of the calcium hydroxide. Okay? All right, one last problem here together. A student used a volumetric pipette to transfer 10.00 milliliters of phosphoric acid, and I notice that that's triprotic, to a solution into a flask. She then filled a burette with potassium hydroxide solution, whose concentration she knows. Now I remember that a concentration like this, 0.1097 molarity, is really a unit multiplier. It means 0.1097 moles per liter. So I can use that as a unit multiplier. She recorded the initial level, and after titrating to the 3rd equivalence point. What does that mean? Since the acid was triprotic, you could have titrated to the 1st equivalence point, meaning you've neutralized one of those hydrogens. You could titrate to the 2nd equivalence point, you've neutralized 2 of the 3 hydrogens. To go all the way to the 3rd equivalence point means you're neutralizing all of the hydrogens. This would be called a complete neutralization reaction. Okay? Depending on whether you went to the 1st, 2nd, or 3rd equivalence point, you would have either a 1-to-1 ratio, a 2-to-1 ratio, or a 3-to-1 ratio. So here, by going to the 3rd equivalence point, we're going to end up with a 3-to-1 ratio in our balanced equation. In any case, when she finished the 3rd equivalence point, the color changed in the indicator, and the final level was 37.02 milliliters. Write the balanced equation. Well, pause and see if you can do that. You want to write a balanced equation between phosphoric acid and potassium hydroxide. Well, if you follow what I did a moment ago, we started by looking at the hydrogens here. There's 3 of them. And the hydroxides here, there's only 1 of them. And we start by making those equal. So since there's 3 hydrogens and 1 hydroxide, I'll put a 3 in front of the KOH to give me 3 of each. Now, each hydrogen combines with a hydroxide, and that forms water. So if you have 3 hydrogens and 3 hydroxides, you'll make 3 water molecules. Whatever's left on the left-hand side is going to be the formula of a salt that is also being produced. So 3 potassiums and 1 phosphate, we get K3PO4. Now, because I used that 3-to-1 ratio, because I made 3 hydroxides for the 3 hydrogens, that's keeping into account that we went to the 3rd equivalence point. If you had only gone to the 1st equivalence point, then you would write 1 KOH, and then you'd make 1 water, and your formula of the salt would have been KH2PO4. If you'd gone to the 2nd equivalence point, then you would write 2 KOHs here. You would make 2 waters, and then you'd have K2HPO4. But because we went all the way to the 3rd equivalence point, we completely neutralized the acid. We neutralized all of these hydrogens with 3 hydroxides. All right, we need a string of unit multipliers to calculate the concentration of the acid. Now let's think about what we can start with. I want to find the concentration of the acid. So what I'm going to start with is the base, because you remember we're going to use the stoichiometry to convert from talking about the base to talking about the acid, which is what we're trying to find. So the base, the KOH, we have the initial and final level. So why don't we start by just figuring out how much base did we use. So 37.02 milliliters minus 1.48 milliliters, and the final minus the initial levels in the burette. This person used 35.54 milliliters of the KOH. Now that's its volume. I have its volume in milliliters. I can convert this to liters. Then I also know its concentration. So if I have the liters, I can find the moles of KOH. When I have the moles of KOH, I can use the balanced equation to get to moles of acid, and it feels like I'm on the right path when I stop and think about that. So I'm going to take that 35.54 milliliters of the KOH as my starting point. Right, so pause the video and see if you can figure out a string of unit multipliers that would end with the concentration of phosphoric acid. So the first multiplier will switch the milliliters to liters of the KOH. Someone who's a little bit more sophisticated might have switched the milliliters to millimoles if they felt comfortable doing that. But I'm going to just switch to liters here. Then I'm going to switch the liters of KOH to moles of KOH, and that's going to use the concentration that we know from the problem. Now that I've arrived at moles, I can use the balanced equations ratio, switching moles of KOH into moles of the phosphoric acid. Now I'm trying to find concentration of phosphoric acid. So concentration is moles divided by volume. So the volume was given at the start. We had 10.00 milliliters. So I'll divide by the milliliters of phosphoric acid. But you remember it's not moles per milliliter, it's moles per liter. So what I'll do is, with one more multiplier, switch the milliliters to liters, and then I'm good. All right? So the first multiplier, 1,000 milliliters in 1 liter. And you'll notice that's the same as the last multiplier, but it's reversed, 1,000 milliliters in 1 liter. So those two things are actually going to cancel out. The second multiplier here, moles and liters, that's the concentration, the molarity of the KOH. So it was 0.1097 molarity, so it's 0.1097 moles for every 1 liter. The next multiplier, moles of acid and moles of base, well, that's the ratio in the balanced equation. 1 mole of acid for every 3 moles of base. Moles we divide by the volume, and the volume of the acid was 10.00 milliliters. I'm not sure if you can hear my audience out there in the hallway, but it's a little distracting. So we take the 35.54 milliliters. I'm not going to divide by 1,000 because I'm going to realize that those things cancel. If you feel like going ahead and dividing, that's okay. So I'm going to times that by 0.1097, and then I'm going to divide by 3, and I'm going to divide by 10, and there's my answer. So we get 4 digits, 4 digits, 4 digits. I'm going to keep 4 digits in this answer. 12996. So it becomes 0.1300 molarity phosphoric acid. All right, now I've been using a string of unit multipliers in both question 2 and 3. Some people prefer to do these in a bunch of steps. They do them almost like we did this data table at the top. And when they do steps, they simply use these formulas: moles equals mass over molar mass, and C equals N over V. I don't really like that method, but it works. If you like that, you can certainly go ahead and do that. The reason I don't like it is people tend not to remember the order of the steps. When you set up a string of unit multipliers, you're not trying to remember the order to do things in. You're simply trying to figure out what to start with. Once you know what to start with, you can basically look at the units, that's why they're called unit multipliers, to figure out where to go next. You're converting one thing into another thing usually. Okay, so I find unit multipliers to be a little bit more straightforward than to try to use those formulas and do things in a series of steps. I hope that helps. Some practice with acid-base word problems for titrations.